and thank you for the opportunity to present some of my work. This talk is mainly about this paper recently published in CCM. So in this talk, the plan of this talk is that first I will start with some motivations from physics and mathematics, and then I will talk about some convergence condition for the correlation functions, and then explain how this uh, convergence condition is compatible with the quasi-Lisse vertex superalgebra. And I will also use some examples to explain some of the main results. And lastly, I will briefly mention about some work in progress about the modularity. Yeah, vertex algebras and their representations are provide a rigorous framework for the two-dimensional conformal field theory. And to any vertex algebra, Arakawa introduced a Cauchy variety. This is a fundamental invariant for the two-dimensional conformal field theory. And this variety reflects the structure, important structure of the original vertex algebra. Uh, if the associative variety is trivial, then the vertex algebra is so-called C2 cofinite, which we have a relatively well understanding. Uh, Beyond that, we can generalize it uh, and allow the associative variety to have finitely many symplectic leaves. Arakawa and Kawasetsu show that genus 1 one-point functions of this quasi-Lisse vertex algebra satisfy modular linear differential equation, and they call such vertex algebra quasi-Lisse. And this is our main object in this talk. And from the physics, we have the 4D, 2D correspondence. And it is expected that all the vertex algebra coming from the 4D theory should be quasi-Lisse. So in this way, we have plenty of examples of quasi-Lisse vertex algebra. So we need to understand some of its general properties. This is one of the motivation. And from the math side, Robert recently proved that the rigidity of the tensor category of grading restricted generalized modules for certain Lisse vertex algebra. And his method uses analytic approach. And this relies on the convergence of the two-point correlation functions, which originated from the Huang Mo and Seibert's idea. Uh, so in other, for the quasi-Lisse vertex algebra, uh, if it is nice enough, then we also expect it to have some nice tensor categorical property like rigid for some nice category. So in order to understand that, uh, one of the essential step is to understand the convergence property of the genus 1 endpoint correlation function of the quasi-Lisse vertex algebra. So this is another motivation of this convergence result, uh, convergence study of the convergence. So as a typical example of a quasi-Lisse vertex algebra, uh, the affine vertex algebra at a admissible level is shown by Arakawa that its associative variety has finitely many symplectic leaps. And in particular, for the simplest example, simplest such example is affine vertex algebra of rank 1 at level -4/3. It has three irreducible modules in category O. But if we just consider the Euro character, only the first one is well defined. The last two are not well defined. So we need to introduce one more parameter, h, the Cartan element, to try to make all these three well defined for the for this uh, flavored character. So we will use this motivating example to try to understand and study the endpoint correlation functions for the quasi-lisse vertex algebra. Uh, so so here uh, I don't give the explicit definition of vertex algebra because it is already introduced in other talk or lectures. So here the analytic intuition of the vertex algebra is the genus zero 3-point correlation functions, and we can insert the elements in the vertex algebra to 3 points. And the composition of the vertex operator corresponds to gluing the genus zero correlation function, genus zero surface together to get this n+2 correlation functions. And one of the most complicated axiom for the definition of a vertex algebra is the Jacobi identity. And from the analytic perspective, Jacobi identity is equivalent to the residue theorem in complex analysis. So our main goal is to try to prove the convergence of the endpoint correlation functions. So here we also want to insert the elements in modules from for each point. So if we insert modules at each point, different modules at each point, it leads to the intertwining operators. And we can also insert the twisted modules. So we get intertwining operator for twisted modules. So yeah, and then we want to prove the convergence of the endpoint correlation functions. So previously we have some condition like C1 cofiniteness and C2 cofiniteness, but we want to try to get a convergence condition which is suitable to the property of the quasi-lisse vertex algebra. So we try to find a weaker convergence condition. So the main idea of the proof is that we consider a linear map from W1 to Wn, which are V modules to a endpoint correlation functions. Then using the Jacobi identity, we can get some kernel of this map. The more kernel we obtain, the weaker convergence condition we will need to assume. Our goal is to try to find more relations in this kernel. And this approach builds on earlier approaches of Zhu, Dongli, Mason, Miyamoto, Huang, and Arakawa Kawasetsu. Yeah, Dongli Mason deals with twisted modules, and Miyamoto deal with one-point correlation functions for intertwining operator, and Huang generalized it to n-point correlation functions. And Arakawa Kawasetsu studied it from the perspective of the quasi-Lie vertex algebra, but they didn't deal with the intertwining operator. So we want to try to get some general result based on this approach. Now we construct. The main idea is to construct such surjective map from C2 algebra module. So RW1 is a C2 module. So it is a C2 algebra Poisson module. And then we try to obtain such kind of surjection. The source is a finite dimensional. If source is finite dimensional, then the target is also finite dimensional. Moreover, we also need to prove that this is finitely generated over a Noetherian ring. Then using L-1 derivative property and construct a proper submodule of this target, we can derive a system of differential equations, which satisfied by endpoint functions. In this way, we can prove the convergence result. And this is the general idea for genus 0 and genus 1. And then we apply this idea to genus 0 and then to genus 1 correlation functions. So for genus 0 correlation functions, Huang obtained explicit elements in kernel of the map we mentioned above. So these are the condition, and this condition leads to the C1 cofiniteness condition, which is crucial to studying the tensor category structure. Now, since I want to get some condition like this, the tensor product of RV Poisson module tensor over C2 algebra and quotient out the Poisson action of RV, G invariant Poisson action of RV on this tensor product. Then I need to try to get something more in the kernel. Here I use the commutator formula twice to get such kind of element in the kernel. If V is a CFT type and self-due, then this kind of relation will give us this quotient, the RV Poisson action on the tensor product. So then, using this idea, we prove that if this quotient space is finite dimensional, then the 4-point functions, genus 0 4-point functions, are absolutely convergent in their respective regions. So this is a condition which this is a condition which is compatible with the property of the quasi-Lie vertex algebra. I will explain later. Then let us move on to the genus 1 correlation functions. So for the genus 1 correlation function, it is defined on the torus. So there are two coordinates for the torus. One is as annulus, and the other one is as a parallelogram. We prefer the second one because we are interested in the modularity property. But original coordinate is chosen to be the first one. So we need to use a coordinate transformation. And this can be achieved by using the notion introduced by Huang, which is called the geometrically modified intertwining operator. And this is similar to the Juice bracket formalism. But this notation is this geometrically modified intertwining operator is slightly flexible in studying the for the endpoint correlation functions. So we use this geometrically modified intertwining operator here. Actually, we can obtain the genus 1 correlation functions from genus 0 correlation functions by gluing 0 and infinity together, and this procedure corresponding to taking trace. But as I mentioned in the motivating example, if we simply consider this Q to L0, uh, for the quasi-lisse for the affine vertex algebra at the miscible level, many objects in the category O are not well defined. So we need to try to insert some simple current for general vertex algebra. So let us give the setup for the genus 1 correlation functions. So here we consider weak G-twisted V modules and also need a Cartan element such that this H0 acting semi-simply on the G-twisted V modules. And we assume that this trace function, this new trace function is well defined for Wn tilde. Now, under this setting, we can study the genus 1 correlation functions. So in order to describe behavior of genus 1 correlation functions, we need to introduce the nice Noetherian ring. And this ring is denoted by R prime. Is generated by the modular forms, including classical Eisenstein series and twisted analog, depending on this parameter. And also we need the elliptic functions and also the twisted analog of the Jacobi forms. Here we need the twisted Eisenstein series and Jacobi form, because here we take the G-twisted module into consideration, and also we insert this Cartan element here. So we need the twisted modular forms. And these functions encode the geometric and analytic data of the torus, and it serves as the natural coefficients for the differential equation we will obtain. We can show that this R prime is a Noetherian ring. So we can try to use our the idea I introduced at the beginning to study the convergence of the genus 1 correlation functions. So again, we want to get something in kernel. So here I omit the some irrelevant terms. So the complete terms are quite looks complicated, but here I only extract the essential piece of the kernel. So these are elements I obtain in the kernel. So here, right, and the second one tells us that we can descend to the C2 C2 algebra Poisson module here RWI. So we can descend to the C2 algebra, and then the third condition tells us that the tensor product, this tensor product is over RV, not over C. previously in Huang's work, uh, he obtained the C2 cofiniteness condition to try to make sure the convergence of the genus 1 correlation functions uh, because the tensor product is over C. Here, since we obtain this kind of elements in the kernel, so we can try we can so design the tensor product over C to OR C2 algebra. And the first type elements correspond to the Poisson action because the zero mode means the Poisson bracket of the Poisson C2 algebra Poisson module. And this is exactly the Poisson C2 algebra Poisson action on the tensor product of the Poisson modules. So yeah, right. So with this kind of elements in the kernel, we can again get such kind of condition. If this quotient is finite dimensional, the space is finite dimensional, then the inter then we consider the intertwining operator and plug in the homogeneous elements in the modules. Then we get the genus one endpoint functions satisfies a system of three type of differential equations in Zi, Q, Qs. Here Q is e to the 2 pi tau, and the Qs is the parameter we insert for the Cartan element, and Zi is each point on the torus. So and the coefficients is over R prime we introduced earlier. Yeah, so here we get that this genus one, since it satisfies the differential equation, then we see this endpoint correlation function is convergent in this region, and it also admits some analytic continuation. So this generalizes the modularity of the one-point functions to the higher point functions. So here we get the convergence condition. Let us now to see how this convergence condition compatible with the property of the quasi-Lie vertex algebra. So here I briefly introduce the quasi-Lie vertex algebra. Uh, it should be its associative variety should has finitely many symplectic leaves. Here, symplectic leaf means maximal subvariety where the image of this map from the structure sheaf to the Hamiltonian vector field given by the Poisson bracket spans the tangent space at every point. And quasi-Lie means its associated Poisson variety has finitely many symplectic leaves. So here, this definition also applies to the super case because for the super vertex algebra, the reduced variety is just our normal variety. The only non-trivial part is its structure sheaf. It has some its structure sheaf is ha has a superstructure. But in order to define the quasi-Lie, we only need this base manifold, which is just the usual variety. So here we have some examples of quasi-Lie vertex algebra. Sorry, example of varieties with finitely many symplectic leaves. And in particular, all these examples are expected to have some vertex algebra correspondence whose associative variety coincides with these varieties. So the first one is a canonical even dimension complex space and a cotangent bundle for smooth varieties and co-adjoint orbits. And the second class of examples are the normal varieties admits symplectic resolutions. Examples include the Nakajima quiver varieties, Lodoy slice in semi-simple Lie algebra, Klein singularity, and Hilbert scheme, and also the cotangent bundle for G mod L n, closure of the cotangent bundle G mod L n. And the last one is the more Tachikawa symplectic varieties. Many of these examples are already shown to be the sociobriety of some vertex algebra. And the most relevant property is proved by Eitinghoff and Schadler for varieties with finitely many symplectic leaves. They show that for any coherent Poisson module over the structure sheaf, this quotient space is finite dimensional. And moreover, the GIT quotient should have finitely many symplectic leaves, and we also have such kind of finiteness result. And this part is filtered algebra with associated graded algebra is finitely generated over its center, and the spectrum of the center has finitely many symplectic leaves. Then this A has finitely many finite dimensional irreducible representations. As we see from this property, this kind of quotient space is very similar to our finiteness convergence condition. So in particular, if we translate this result in the under the VOA setting, we get the following. If V is quasi-Lisse vertex superalgebra, G is the finite group of the Poisson automorphism of C2 algebra, and if M is the finitely generated RV module, then this quotient space is finite dimensional. And if we consider the G invariant space, we also get some finiteness result. So we can use this result to try to get the convergence condition. For example, if all the RV modules, let's see. If all these RWI are finitely generated, then this tensor product is naturally finitely generated over RV. Then, according to the result by Eitinghoff and Schadler, this quotient space should be finite dimensional, and the convergence result follows. Now let us try to see some concrete example. So if we specialize our genus 1 endpoint correlation function to genus 1 point correlation function, and we choose the W to be V and the element in V, we choose it to be identity, and this Cartan part, we choose it to be e to the 2 pi I sigma. Sigma is the parity automorphism. Then this genus 1 correlation function coincides with the super character of the module, W tilde. And moreover, if we consider the quasi-Lisse vertex algebra, this condition is automatically satisfied. So it tells us that if V is quasi-Lisse, then the super character of any simple G-twisted V module satisfies a twisted modular linear differential equation. As an example, Bin and Rastelli showed that the vertex operator algebra coming from the n equals 4 super Yang-Mills theory, their character satisfies this twisted modular linear differential equation. Right. So this is the convergence part. And by using this result by Eitinghoff and Schadler, this last piece, we can prove that if V is quasi-Lisse, then V admits finitely many simple ordinary G-twisting modules. Previously, Arakawa and Kawasetsu showed that if V is quasi-Lisse, then it admits finitely many ordinary modules. Here we get finitely many G-twisted modules. These ordinary G-twisted modules include more objects because from our motivating example, L negative 4 over 3 SL2, it has 3 elements in category O, but only one ordinary modules. But if we consider the Z2 twisted modules, then all of them are in our in this belongs to the ordinary G twisted modules. So this, yeah, right. So here I omit the idea of the proof. Yeah, if we assume that RWI is finitely generated over RV, then of course we can get that this space is finite dimensional. But if RWI is not finitely generated over RV, we can still, in some cases, to get the finiteness for this quotient space. In particular, I showed that if we consider the highest weight modules or their controgradient modules for LK-SL2, this quotient space is finite dimensional. As we know that this LK-SL2 general highest weight modules are not necessarily finitely generated. Their C2 Poisson module is not necessarily finitely generated over RV, but we can still show this quotient space is finite dimensional. One of the key ingredients is the nilpotency of the conformal vector in RV. So it is interesting to try to find more examples such that this condition is satisfied so that we have the convergence result. Then I will talk about some work in progress. So previously we studied this genus 1 endpoint correlation functions, and we also insert this Cartan part. Geometrically, this Cartan part is expected to be related to the line bundle over the torus. So then we can consider the conformal block, but twisted by a degree 0 line bundle. Then we can consider this conformal blocks twisted by line bundle. And we expect that all these genus 1 endpoint correlation functions should yield a linear function, which is a conformal block in this in our sense. Moreover, if the quasi-Lisse vertex algebra is nice enough, so here we take the stable category into consideration. So basically says that if we change the conformal vector a little bit, we would get some semi-simple category. This is true for the affine vertex algebra at the miscible level. If we shift the conformal vector a little, then we would get some ordinary modules and also semi-simple category, which is in some literature called the Q rational. This is our expectations, which is still work in progress, is that if this if the finite dimensionality, if the finiteness condition I obtained, the convergence condition, then we have the finite dimensionality for the conformal block for the quasi-lisse vertex algebra twisted by a line bundle. And moreover, this we assume this V to be Q rational. And we also expect that the genus 1 twisted endpoint correlation functions should have some modularity property by using the convergence result. And hopefully we can get some conceptual way to understand the Valinda type formula in this setting. Thank you for your attention.
Thank you very much. Are there questions? Any questions? So maybe I have a question. So you said if it's quasi-lisse and you only have finitely many modules of some sort, but then you also get infinitely many modules of some other sort. How did that?
Yeah. If V is quasi-lisse, then it has finitely many ordinary G-twisted modules.
Ordinary is where the grading is bounded below.
L0 space is finite dimensional.
Oh.
Yeah.
And then you get an infinite number of additional modules where that's not the case.
But we want to. Yeah, but we focus on this simple ordinary G-twisted modules. Yeah, if we take all the modules into consideration, it will be quite complicated.
Right. And these close under fusion operation, these modules?
This is still open, that if the quasi-lisse vertex algebra admits a braided tensor category, this is still open. Yeah.
Thank you. Are there further questions? If not, let's thank the speaker again. Thank you very much. I'm supposed to continue straight away with the second